Okay, so electrolytic cells, this is our warm-up today. We have, what they do is they dig up this ore from the ground called bauxite and they melt it. Okay, and they actually mix it with another aluminum compound called cryolite because the mixture has a lower melting point and that saves them energy. Hooray, right? Saving energy equals saving money. So, but essentially it's liquid aluminum oxide. Okay? So the only thing, and 2 carbon probes, right? And a battery. So, but the battery alone tells us that this is the positive end, which makes it in an electrolytic cell, the anode. And this is the negative end, which in an electrolytic cell is the cathode. And I'm just going to change this marker because it's not very good. And so the anions are going to the anode and the cations are going to the cathode. What are my anions? O, 2 minuses. So they're going to the anode. And the cations are going to the cathode. And the cations I have are my aluminum 3 pluses going this way. Right? And so the aluminum 3 pluses will get to that cathode. They will gurk when they get there. Right? How many electrons do they gain?
3.
3 electrons, and they become aluminum liquid because it's hot. And so you get this drip, drip, drip forming on that probe. In fact, actually, I kind of lied to you. They make the whole bathtub. They just hook this whole thing up to the bathtub and make the whole bathtub the cathode. But I thought that looked a bit funny at first for you. But do you understand how they do that? So the whole thing, the whole big metal bathtub is electric. So anyway, but drip, 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 and then they have a little tap down there, and they siphon it out into a bucket, not really, a big vat, and they then solidify it, and you get your aluminum bars. Everybody happy with that? Everybody get that side of the reaction? So this is your reduction half reaction, this is happening at your cathode, and it is the strongest oxidizing agent that is present. The only other thing to happen is the oxide, really at this point. Okay, so the oxide, O2 minus, is going to become O2, oxygen. And how many electrons is this one going to have to give up in order to become neutral? 2 electrons, but I need to form 2 of them that join up together. So I need 2 of these O2 minuses. So therefore I would need 4 electrons, and that's my half reaction. That might be in your data booklet if you're lucky. Then you don't have to kind of figure that out on your own. And this is your LiOA, your reducing agent. And so we're making nice fresh oxygen. Not really, actually. The oxygen reacts with the carbon electrode and then makes carbon dioxide, and then the carbon dioxide goes into the atmosphere. So it sounds like a really healthy factory, but it's not. And then they have to replace the anode every once in a while because it deteriorates, because the oxygen reacts with the carbon. So quite an expensive operation here, right? You've got to heat that rock up, you've got to replace your anodes on a regular basis. Quite an expensive operation. But because aluminum's quite cheap, really, so they must, so they make enough of it in big vats, and the raw material is cheap enough. Yes.
Did you change carbon out for something to make it a little less polluting?
Well, you could change the carbon out to, what could we change the carbon to? Platinum, because platinum, the oxygen would hit the platinum and then do nothing, right? And that'd be great, except for these big, like this bathtub, we're talking about is like as big as this room, and my factory would have 20 of them. And so what you have for these anodes isn't just one stick, but actually it's a whole like sandwich of sticks that they then drop in, right, and then pull up and replace them. So to have that much platinum, essentially it's a wall, right? You drop a wall and a wall and a wall and a wall. To have that much platinum, it's too expensive. So they don't do it. Which is then when you get into the social studies aspect about how, well, what kind of taxes are there for how much carbon dioxide your factory is producing, And then that tax money means something to them, because they then have to pay on top of. And so the offset cost of that tax compared to the use of the platinum is then a delicate balance that they need to figure out at what point do they start using platinum or another inert electrode. Does that make sense? And so, and not just this factory company, but any environment tax forces companies to start to make that balance and adjustment, to make it less cost effective to be unenvironmentally friendly, and more cost effective to be environmentally friendly. Because when push comes to shove, that's what they care about, really. That's what I would care about if I owned $1 billion company too. Yes?
So we found the Gherk by going to the table and finding, like, doing the finger thing? Like where
Well, yeah, sure, but there's only two things.
Okay.
So there's only two things that exist. So it's a bit of a waste of time. You can go to your data booklet, but it is a bit of a waste of time. That's the only thing that can gain electrons. This is the only thing that can lose electrons.
Okay. But
So,
like the science behind the oxygen, is it because it has the highest affinity for electrons out of all our entities?
no, because right now I'm losing my electrons, not gaining.
Okay. Well, why can't it be carbon?
Because carbon's the state.
Carbon's inert, so it would be a very, 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 very weak oxidizing agent, a very, 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 very weak reducing agent, and it would not play a part in our species list. It would be a spectator,
Okay.
as platinum is. Happy, everybody? Okay, so that's a little bit of a warm-up, but I actually forgot. I've got the Hoffman apparatus here. It's filled with water. Jordan, is it filled with water?
Yes, I can verify that.
Good. So glad. I'm going to turn it on. Jordan, could you also verify that there are now bubbles coming off these platinum electrodes?
Yes, I can see some.
Okay, and I'm going to let that run all class, and we'll talk about it at the end of class. Okay, the electrolysis of water. I just turned that thing I turned on was a battery. So there's a battery pack, flick it on, and I am electrocuting water right now. Over there. Okay, but it takes a while for those bubbles to form and for us to actually see anything, any stock of bubbles. So I'll just let that run and we'll talk about that at the end of class.
So if
Happy?
we were able to touch the water, would we feel it?
Good question. Never tried it.
Can we try it?
No. I could lose my job.
I volunteer.
If I get to choose the student. No. No, I don't think you, well, that's a good question.
Or would it get stronger over time, maybe?
Yeah, I suppose you probably could feel it slightly. Yeah, why not?
Is that kind of like when you drop a hairdryer in a bathtub or something?
No, not quite as strong as that. Not quite as strong as that. Okay, so, can you understand that how much power I turn this battery up to, speaking of which, I should just make sure, how many voltages I have on that battery, or how many voltages I have on this battery, will determine how many electrons are coming out of this anode, out of that battery, to the cathode. So the power on that, I'm going to say power, the power on this battery will determine how many electrons are flying out of here. Everybody okay with that? And the more electrons I have flying out of there, the more electrons can be adding on per second to this aluminum 3+. So therefore, the more aluminum I'm going to make per second. Does that logic ring true for everybody? Does everybody get that sense of logic? The more electrons that fly out of here, the more often I can have that happening, the faster I can make my aluminum. Okay? What we're going to do is we're going to put actual numbers to this. If I want to make 5 grams of aluminum, what power do I have to be coming out of my battery in order to do that? And by power, I'm going to now start talking about amperage. So amperage, well, in fact, actually, let me just call up the slide. So in your packages, that's what we're doing on the side there, the electrolysis of water. So we're just going to go back to that in the class. Oh, whoops. In your package, you have a category that's called cell stoichiometry. So this first couple paragraphs is basically saying how many electrons the battery provides will be proportional to how much metal I can make. The more electrons, the more metal I can make. Everybody get that? The less electrons, the less metal I can make. Okay, so at first the number of electrons could not be calculated. And so scientists could only measure charge. Charge is Q. Those of you that are in physics are going to be like, yeah, I know. Those of you that aren't in physics need to really grab this by the horns. So sadly, Q now means two things for us. Q from unit 1, Q equals mc delta T. And now we've got a second little q, which is now meaning charge. And just to make things even more complicated, the first q from unit 1 was in joules, and this q is in coulombs, neither of which really makes sense. Q does not sound like joules, and q does not sound, well, it sounds like coulombs, I guess, but doesn't have a big C. So the units when you solve for q is charge in coulombs with a capital C. Everybody okay with that? Okay? Coulombs equals amperage times time. Because time is in seconds, and how many amps you have is how many coulombs you have per second. How much charge you have per second. Okay? So, here's my battery. I want to know how much power it has. And I mean power in a loose term, like how much strength it has. Okay? So in order to figure that out, I would love to be able to see those little electrons. And if I see the electrons going out, 1 electron, 2 electrons, it doesn't sound very strong to me. But if I have 10 electrons per second, that sounds like a strong battery. Does that make sense? And that's what this is. Strong battery is coulombs. How many coulombs per second is how much amps I have, how much current I have. 10 electrons per second, 20 electrons per second, 100 electrons per second. Do you see that? Only electrons aren't little things, right? They're not little circles. They're clouds. Oh my God, right? How do you count clouds? You can't. But you can count how much density a cloud has, how thick the cloud is. And so that's a charge, how much charge the cloud has. Okay? So if I have this much charge per second versus this much charge per second, that's my strength of battery. Everybody get it? That's what amperage is. How much charge I have per second. And then if I run that battery for 1 second, 2 seconds, 3 seconds, that's how many coulombs, or Q, came out of my battery. Make sense? So how many electrons I have flying out per second. But of course I can't count those electrons, they're rather density. So how much charge I have coming out per second, times how many seconds I ran the battery for, will tell me the total charge that came out of the battery today. Okay, how much cloud came out of the battery today? Everybody okay so far? Okay, because it's not done. So that's all they could really do, is they could measure how many amps on an ammeter. They could measure how many seconds on a clock. And they multiply the two together and they could tell you, oh, that's how much charge came out of the battery today. Okay, but they didn't kind of know how that equated to how much silver we made on our trophy. Okay, so, or how much aluminum we made in our vat. So in the 1830s, Michael Faraday, oh yeah, he really, what?
Too far.
Where am I?
Go at the beginning of
I'm at the beginning. Gee. So Michael Faraday came up with Faraday's constant. Are we here yet? No. Sorry, guys. Okay. Da, da, la, la. Okay, so because we would love to count the number of electrons. If we can count the number of electrons, then we can put it in our half equation. Okay, the number of electrons. Because remember stoichiometry? Don't go down the column, across the bridge, down the other side. Remember that? That's what we're about to do here. But I have to know a number of electrons. But I don't have a number of circles at the moment. What I have is charge, these big clouds that come across. So Michael Faraday started to relate how much, if I have this density of a cloud, or that charge, how many circles should we probably draw for our electrons? Does that make sense? A little bit like Avogadro saying, I have 1 mole. How many circles is in that 1 mole? 6 times 10 to the power of 23. Remember? So it's sort of the same thing, but Faraday said, instead of if I have a whole mole of clouds, how many circles, if I have a mole of circles of electrons, how dense is that cloud? That's what Faraday started to ask. And so he came up with this. If I have a mole of circles of electrons, 6 billion trillion electrons, that cloud will be 9.65 times 10 to the power of 6 coulombs. This is how dense the cloud is if I have a mole of electrons. Does that make sense? So if I have 2 moles of electrons, it'll be twice as dense. Okay? So, we know how much amperage is coming out of our battery from the ammeter. We know how many seconds we've run that battery for. So therefore I can know how much charge came out of my battery. But I don't actually know what that means in terms of circles for electrons. So Faraday said, hey, do you know what? If the charge that comes out of that battery is 9.65 times 10 to the power of 6, so that's 9 million, right everybody? Question mark? 1, 2, 3, 4, 5, 6, 9 million. If I have 9 million coulombs, I'm going to count that as a mole. There's 1 mole. There's another mole. Okay? Get it? So how much charge is coming out per second? How much charge do I have total? And if that is 9 million, I'm going to say that that's 1 mole of electrons. 6 billion trillion circles of electrons. Okay? Whereas for something physical, like carbon, 12 grams is 1 mole. Right? Oxygen, 32 grams is 1 mole. But here I can't take a mass. I've got to look at the amperage coming out of my battery. Okay, so for those of you that like math formulas and plug it in, you can now listen and ignore all the stuff I just said. So, number of electrons is equal to the charge divided by Faraday's constant. Okay? Because the charge is how many coulombs I have out, and Faraday's constant is coulombs per mole, and so coulombs divided by coulombs per mole will give me how many moles of electrons I have. If I have 2 moles of electrons, I would multiply that by Faraday's constant to find out how much charge I have in total. Everybody okay with that? And a reminder that coulombs is equal to amperage times time. That's important because quite often I can just get the amperage from my ammeter, get the time from my watch. So I'm probably going to use this formula the most often. The amperage times the time divided by Faraday's constant to get number of moles of electrons. Okay, but sometimes they give you the charge, the coulombs, right from the beginning. So you have to know Q divided by F. Yes, you have to memorize these. Taken Physics 30, hands up. Already have it memorized?
Yep.
Yeah.
Where does the I come from?
Amps.
Instead of A.
So how much, pardon me, instead of A.
Okay.
Yeah, I know. Leave it to the physicists to make things confusing. Right? It's not my world, it's their world. Okay, so, yeah, I don't know why actually. Probably because
Used for something else.
A was used, yeah, but I can't think of anything it was used for, so maybe it's Latin, maybe they don't say amps in Faraday's world.
Use.
Imps.
Imps. Is
Okay.
he like German or something?
Sure. So here's an example. How many electrons in moles flow in a 3.0 amp system that runs for 2 hours? Well, the first thing I have to do is I have to convert that 2 hours into seconds, right? So times 60 times 60, and I get 7,200 seconds. So 7,200 seconds times 3 amps, which is coulombs per second, divided by Faraday's constant. And I've done the unit analysis here for you, so you can see how the seconds cancel out and the coulombs cancel out, and I'm left with 0.22 moles of electrons came out of that battery today. Does that make sense? Okay. So, if I know how many electrons, number of moles of electrons that came out, I can figure out how much solid I've made. So here's a bumper, and I'd like to electroplate my bumper. So chromium bumpers, like on cars, right? Chromium metal is pretty soft. Do you want your bumper to be nice and soft? Not really, right? So they have an iron bumper, because that's hard and sturdy, and then they electroplate chromium on the outside, so it's lovely and shiny like chromium is. Okay? So imagine this big bumper being placed in a vat, just like we had our trophy placed in a vat in our warm-up today, and we're going to electroplate chromium onto our steel or iron bumper. Okay? So that's what all that says, and I turn on my system. It says that 9.8 amps are flying out of that battery, and I'm going to leave it on for 20 minutes. Electroplating chromium on a steel bumper. How much chromium was produced in this time? I'd like to know the mass of chromium made at this time. So in Chem 20, and in our titrations for Unit 1, we started off with a balanced chemical equation. Right? Here I'm only going to do a half equation, balanced half equation. So here's my balanced half equation. Chromium 3+, because that's what's in my vat, a bunch of chromium ions, and I'm going to make chromium solid. Every okay so far? The information about the battery is going to go underneath my electron column. So time 20 minutes, amperage 9.8 amps. I'd like to know the mass of my chromium. And we're going to go down the column, cross the bridge, down the other side. So how many number of moles of electrons came out of my battery today? Well, number of moles of electrons equals IT divided by F. The I is 9.8. The time in seconds is 1,200. You need to remember to convert it to seconds. Divided by Faraday's constant. So I have 0.12 moles of electrons coming out of my battery today. Okay? So 0.12 moles of electrons coming out of my battery, and that will be proportional to how much chromium I get to make today. It's a 3-to-1 ratio, right? 3 moles to 1 mole. So I need to take my number of moles of electrons and divide it by 3, or multiply it by 1/3, and I get that many moles of chromium made today. And then if I have number of moles of chromium made, I can figure out the mass through the lovely, very simple Science 10, number of moles equals mass divided by molar mass. And so you take the number of moles, you take the molar mass, you multiply them together, and I got 2.1 grams of chromium made today. Does that make sense? Any questions on how to do that? Okay. So I have for you, we could start with these practice problems, but in the interest of time, because it's Friday, I think we'll just jump straight to these questions. Okay? So we're going to jump straight to these questions, and you're going to do a bit of work on these stoichiometry, cell stoichiometry questions. So the only thing that's different is we have a new formula for number of moles for our electrons, and we're only having a half equation, not like a lovely full equation. Okay? Any questions?